Hello, everyone. So welcome to this industry spotlight talk session. And as a tradition, this is a very exciting session, and we're going to have 4 distinguished industry speakers in this session. So I'm Kun. So this session will be chaired by me and all my colleagues. So let's have the first speaker, Gil Bloch. Gil Bloch is a senior principal architect at NVIDIA, and he leads a global team responsible for the software and the system architecture for large-scale AI system. And his work focuses on building high-performance, scalable infrastructure for distributed AI training and inference. And he with an emphasis on co-design across the computer, network, and software layer. So welcome, Gil. Yeah.
Thank you. Let's see that everyone is coming in. Okay, I'll just start. Thanks for the introduction. My name is Gil. The title was a bit long. We don't really use those titles in NVIDIA. I'm going to use the first 2 minutes, I'm just waiting for the movie to start. I'm going to use the first 2 minutes to show you, most of you have seen this movie from GTC, so that more people will come in.
A visionary.
And then I will try, I have 30 minutes, 150 slides. Bear with me, I'll be fast.
Illuminating galaxies to witness the birth of stars.
I don't think I still need to convince you how important AI is.
And sharpening our understanding.
I don't think I need to teach you how many different applications there are for AI. It's a part of our lives already.
I am a helper, guiding the blind
but still,
through
let's
a crowded world.
Give it 2 minutes, and I'll start with my talk. During my talk, I'll try to go through basically
and giving voice to those
a quick overview of what we do, and then emphasize one issue that needs to be solved to really enable
a
AI.
Transformer, harnessing gravity to store renewable power. And paving the way towards unlimited clean energy for us all. I am a trainer, teaching robots to assist, to watch out for danger, and help save lives. I am a healer, providing a new generation of cures and new levels of patient care.
Doctor, that I am allergic to penicillin. Is it still okay to take the medications?
Definitely. These antibiotics don't contain penicillin, so it's perfectly safe for you to take them.
I am a navigator, generating virtual scenarios to let us safely explore the real world and understand every decision. I even helped write the script. Breathe life into the words en muchos idiomas y escribí la música.
Okay, I will stop here with the orchestra playing. A quick translation for those of you who do not speak Spanish. Y escribí la música means, and I wrote the music. The music was written by AI, played by a real orchestra. And I want to start with that. Let me just move to the presentation and talk about the orchestra. I was trying, by the way, to learn the names of those local instruments. Too hard for me, I'm sorry. But I want to talk about orchestra before we talk about AI and GPUs and whatever we want to talk about. In an orchestra, you have many instruments And the most important part for it to sound like music is synchronization. They have to play together. If each one of them plays separately, it sounds terrible. And the reason I'm saying that is that when you build an AI factory, where you try to train LLM, when you try to create, serving system, putting thousands or tens of thousands or hundreds of thousands of GPUs is a nice thing. It just doesn't help you. If you don't connect them to be a single computer, a synchronized computer, it's worthless. So yes, we are NVIDIA and we do GPUs, but I'm here to talk about the network. The network is what defines the supercomputer. The network, the connectivity, the data transfer, it's what allows you to take tens of thousands, hundreds of thousands, maybe millions of GPUs and make them a single computer. It's not trivial. And the network is not trivial. And we are all here talking about networks. You've heard probably a lot of innovation in the last 2 days around how network can be optimized, how we can make our network more efficient, how we can estimate network performance. Network is a complicated thing, and network is what defines the next generations of supercomputing. So when talking about the network, it's actually not one network. In common supercomputers today, there are 3. There is the scale-up network, the memory. Well, usually I don't like to call it network. It's more of a memory bus or memory network. It's the scale-up. NVLink, it's very interesting to see that modern supercomputers are building bigger and bigger scale-up. Those of you who've been with HPC for a long time, we were trying to build very large-scale scale-up systems, and then we have realized that it's a mistake, and we moved to scale-out. Scale-up is back, and scale-up is back for multiple reasons. One is performance, the other is programming models. Scale-up is there, and we can show that scale-up helps improving performance for both inference and training. So scale-up, again, NVLink switches, NVLink system. Scale-out, east-west network. Most of us, when we talk about AI networks, we talk about east-west. I'll talk about the east-west in just a few minutes. And there is also, don't forget, the secure access, storage, management, north-south network, DPUs, security. Those are just as important. Not the same tasks, but just as important to make the orchestra, to make this symphony work. If you don't have everything together, it just doesn't work. So I want to focus for just a few minutes on scale-out, right? So with the scale-out, again, a quick update. We have basically 2 technologies that I'm going to talk about, InfiniBand and SpectrumX. InfiniBand, I don't need to say what InfiniBand is, just a quick one. We have InfiniBand, high performance, in-network computing, all the goodies of InfiniBand. In-network computing basically effectively doubles the bandwidth. How? By doing things in the right place. Instead of doing computation in the edge, moving computation into the network just gives you effectively double the bandwidth because you just don't have to move data too many times. Not going to focus on that. SpectrumX. People have been doing Ethernet for many years. It's not new. People have been connecting hundreds of thousands of servers with Ethernet, building cloud data centers. But we need to remember, cloud data center is a totally different thing. In cloud data center, most applications are loosely coupled. One VM that runs on one server will not communicate with other VMs on other servers. This east-west traffic is not there. And even if it's there, it's not as tightly coupled as in a supercomputer. In a supercomputer, in an AI factory, if there is a delay, everyone waits. Since you need synchronization, even today's most algorithms requires synchronization, mostly in training, but also in inference. If one processing engine is delayed, everyone is delayed. If a message is delayed, everyone is waiting. You can build a 1 million GPU system and have 1 million GPUs waiting. It's not the most efficient way to use your GPUs. On top of that, different transports, different protocols. If the cloud used to use TCP, which is high latency, resilient to distances, it's different when you need to use that for AI factories, RDMA, RoCE. So the requirements from Ethernet has changed. Ethernet today is not the same Ethernet that connected 100,000 servers in a cloud data center. It's a new Ethernet. We call it Spectrum-X. There are different names in the industry, but remember, it's a new Ethernet that is required for AI. One most important thing, again, as I said, each delay means you have many GPUs waiting. So you don't really care about, if you run the benchmark and you see a number for all reduced 10 microsecond, this number is, let me tell you, is average. The benchmarks, what they do is run many, many times and average that. Not only that, most benchmark will first do a warm-up. They run a few cycles of all reduce and only then start measure. So what you see is kind of an average with cleanup of, the first iterations. Sorry. So in AI, this is not the number we care about. In AI, the number we care about is the long tail, right? Let me show some numbers, some example. Sorry, wrong side. Basically, when you measure, you have many measurements, right? You run many times, you show the average. I don't care about the average. What I care about is the few times that I get bad numbers, the tail latency. Because for each time that I get one of the GPUs or one of the iterations is delayed, it means that I have all my GPUs waiting and not processing. What we show, measured, is that when you use Ethernet, sometimes you get very good numbers. Sometimes you get higher numbers, and sometimes you get very high numbers. And when you use Spectrum-X, when you use our AI Ethernet, you can see in the green, you don't have the tail latency. You get almost all measurements with the same latency. This allows you to have an efficient, not just good average, but an efficient AI factory. So what makes our AI Ethernet different? Couple of things. I'm not going to go through everything. Tail latency, most important one. You need to make sure that the latencies are not just nice in average. You need to make sure that the worst measurement is still a good one. You need to make sure that you don't lose packets. If you lose a packet, there is an inherent delay for a transmission. You need to make sure that you don't have hotspots and congestion, because if you do, there are delays. You need to tune your network for very high load. All of that comes with Spectrum-X. So again, Ethernet, right? But it's AI Ethernet. And I think the most interesting thing is, hey, it works. This is where I'm proud to show that. XAI built a 100,000 GPU system, AI system, in record time and ran training on the system. Look at the numbers. From the day they rolled the first rec to the day they trained AI on the system, 19 days. Whoever here had the chance to try and test new system? I think it's amazing. For me, it's like magic. Being able to connect power and run training in days is magic. To do that, you need a system that is already tested, a system that works, a system that is tuned, and a system you can get good results. 95% efficient bandwidth on a system that took 19 days from rolling the first servers to actually training on the system. By the way, XAI, it's easy to talk about XAI for a reason. Elon Musk is known to love to tweet, right? Everything that he's doing, you can see publicly on his Twitter. And I'm going to use that. I can tell you it's not the only large-scale system. It's just the only public one. Not even the only public one. By the way, OCI also published that they are building a 130,000 GPU system using Blackwell. They did not say the date, but they say that they build this system. Back to XAI, 100,000 GPUs. Anyone knows how much power this system consumes? 150 megawatts. It's not official, but it's probably pretty accurate. He also said that in this year, 2025, it will be 200,000 GPUs, about 300 megawatts. And he also said he's going to upgrade it to 1 million GPUs. I can only estimate 1 point something gigawatt for a single supercomputer. It's a challenge. Anyone knows how much power consumes El Capitan, the supercomputer that in the top of the top 500 list? No one. 30 megawatts. I know, too many numbers. Let me just take that and move to the next slide. In the old cloud systems, the transceivers, right? We are back to networking. The transceivers connecting different servers consume 2.5 megawatts for 100,000 servers. If you go to servers in AI factories, it's servers, not GPUs. 100,000 servers is about 40 megawatts, just for transceivers. 30% more than the top 500, number one in the list, power consumption of El Capitan, is going to be consumed by transceivers in the next generation AI factory. It's a problem that we cannot ignore. We need to find a way to do that way more efficiently, otherwise it will prohibit us from getting to the size that we want to get. And this is what I wanted to talk about. All that, you know, the music, the instrument, it was all to get to, hey, we need a more efficient way. And this is what I'm going to talk about here. So, old ways, right? You have a chip, electrical signal going on the PCB, you have a cage, and you plug in a pluggable module, optical pluggable module. All switches do that. We will not. If you have already seen, Jensen, our CEO, introduced our new technology, well, new. He introduced co-packaged optics, so we take optics directly out of the package of the switch silicon, and instead of electrical, we go optical all the way out. This is what you see here. It looks like a small thing, but it's not. Basically, it allows us to reduce the power from 30 watts to 9. 3 times reduction in the power consumption. Again, 40 gigawatt to a bit more than 10. It's savings of a lot of power. You can do 2 things with that. Either you reduce the power consumption of your entire system, which no one will do. The way I've seen, what it means is people will just put more GPUs. Now you can trade the power that was lost on transceiver and gave you no compute benefits into more GPUs, more compute in the same power that you can provide to the system. Basically, people will build systems as large as they can put the power for. People plan more than 1 gigawatt systems. It's going to be a challenge. It's going to change the way we provide power to systems. Already today, we build generators for specific computers. We don't just connect them to the power grid. People will generate power and use that for GPUs and compute instead of for transceivers and waste of power. So CPOs, as I said, about 1/3 of the power consumption. This is not the only benefit. Another benefit is basically better signal integrity. If you look at the old way, you know, each time you have to take your signal from one place to another, you get penalty. So you had to go from the switch ASIC to the substrate, to the PCB, to the port cage, to the DSP, to the... We save all that. We go once from the switch ASIC to the silicon ASIC, the silicon photonics. That's it. So you get much better signal integrity in much less power. This is what we want. This is where we want to get. So NVIDIA photonics, you know, it's not a new science. People have been looking at photonics and co-packaged optics for a long time. So why am I talking about it now? Because it works. We now have working systems with CPO. It's going to be in production next year, 2026. You will see systems built around CPOs, saving a lot of power for the network and allowing you to use this power for compute. You know what? I'm going to skip that. I want to leave a few minutes at the end. How much time do I have? Okay, so I'll leave a few minutes for questions and 2 minutes at the end. There is an exam, by the way. I hope you remember all the numbers I said, right? 40, 30. Anyone remembers what was the 30 megawatts? Just me? Wow. Number one supercomputer in the world, top 500, El Capitan, 30 megawatts. We can save 30 megawatts out of the next generation supercomputer, right? We give you a new #1 top 500 supercomputer just by moving to CPOs. So you can look at that at multiple ways. Either how many more GPUs you can connect with the same power that you allocate for the network, or how many laser modules you save. There is a lot of saving here, but bottom line, we are going to make the network way more efficient. We talked about latencies and jitter and tail latency. Most important, we will save network power so that you can put more compute in the same power. Let me just conclude that and give you a few minutes to ask questions. The easy questions, please. The hard one, you can find me after the talk, and I'll be here and be happy to talk. But if anyone has an easy question, I'd be happy to take that.
Okay. Thanks for the talk. So we have time for a few quick questions. Go ahead.
Yeah, thanks for your good presentation. There are two questions for me. The question is about the SharpV4. Yeah.
Okay.
Yeah. I want to know how many GPUs are supported using the SharpV4. That's the first question for the skill. And the second one is that for the AI model training scenarios, which is using the scale up and the scale out networking, and the most part of traffic, such as TP or EP or SP, is in the scale up network. But and for DP, which is running on the scale out network, for SharpV4, it's using from my understanding, which is used for the scale out network. So, but the DP part it's a lower in the lower part of the traffic. So I wonder in these scenarios, what's the benefit of the SharpV4 for this scale out network? Yeah. Thanks.
So I'll try to give a quick answer. SharpV4 is, the main benefit of SharpV4 compared to the older versions. We've been doing all reduce for many years. Unfortunately or fortunately, today's sophisticated models just don't use all reduce. They use reduce, scatter, all gather because you can now distribute the optimizer. And the main benefit of SharpV4 is to enable you to do that while still benefit from the 2x bandwidth, since we can do all reduce, scatter, and all gather overlapped on the same network, which doesn't work with any other algorithm but Sharp. That's the benefit of it. In terms of scale, basically it's unlimited. Sharp is scalable because it's hierarchical. You just add more switches, so it gives you more connectivity to more GPUs. The benefit, there is huge benefit for FSDP. FSDP is using reduce, scatter, all gather, and we show that we can overlap that. For 3D parallelism, there is benefit, but not as large. Now, for more details, please catch me afterwards. Thanks.
Thank you.
So, have more questions? Yeah. So actually, I got a question for you. Yeah. So you talk about this silicon photonics, right? So I have the integrated silicon photonics in the chip. So compare with the currently pluggable solutions, how do you think about these reliability issues? If that any, we have a high failing rate of this pluggable optics. So if it's integrating the chip, what happens for the reliability?
So yes, it's a challenge. Currently, what we show in our lab that it has great reliability numbers. I'm not coming from the physics to explain why it is, but I can say that we do have testing that shows great reliability in time. Obviously, it needs to be cooled, right? I think a large number of the issues people have with optics reliability is basically cooling issues. I think that's the short answer.
So actually we have time for one or two questions, short questions, yeah. Oh, okay. Well, yes, yeah.
Thanks, Gil. Wonderful presentation. And I have a very short question. What do you think about the boundary between the scale-up network and the scale-out network? Because originally, most of the inter-host connection, what we call scale-out, right? Like RDMA, but nowadays in supernode, within a supernode, most of the internode connection are replaced by the scale-up connection. So what do you think about the boundary, and how will this boundary evolve? Thanks.
So I think the first thing we need to open here is, what is it that you call a node, right? In the past, a node was two things. It was packaging, you package a node, and it was single OS, operating system. You had an operating system for each node. Those two things are no longer that interesting. No one cares about the packaging, right? You build a rack, and if there are 8 nodes or 10 nodes, so this has changed. And the second thing that we are now changing is that we actually no longer care much about how many operating systems you run. If you look at the new way we do scale up, basically, well, we call it multi-node. I think it's a wrong name, but we call it multi-node NVLink. What it means is that we actually use, just like partition global address space, we allow you to map a virtual address space on top of multiple OS domains. So the way I see it, you just have a larger node. You have a very large node, 72 GPUs in a single node, single address space, doing shared memory basically, right? I'd say what defines a node now is the shared memory domain. Even if it's partition shared memory, it still is shared memory. So we just build you a bigger node. What I call a node is your shared memory domain. We build bigger and bigger shared memory domains because the application requires that. You know, it's not that we do that for fun. Applications benefit much from having large-scale shared memory domains with high bandwidths, and this is what we build. So today it's 72. I think it will keep growing. I think there is a limit to how far you can grow with shared memory domains. History showed that before. But we will see, many things may change.
Okay, thank you.
Yeah, we can have these discussions on the panel. So just come to the panel, so if anyone want to. So actually, we got the time. Thanks, Gil, and
okay.
We have.
Thank you. Thank you very much.
Okay, so there comes the second.